forgot that it's 12 o'clock, so I wanted to go ahead and get started. So Cynthia has plenty of time for her webinar today. Just want to welcome everybody to North Carolina ASA Data Science webinar series, and many thanks for attending. My name is Susan Simmons, and I am VP2 of the North Carolina chapter of the ASA. And we are very excited to partner with our industry interest group to bring you this webinar today. We've got a great lineup of webinars for next year, and I encourage all of you to keep an eye on our website and social media accounts to see what interests you and attend those activities that you can. The North Carolina chapter is one of the largest ASA chapters, and we have a really active community with lots of events. Please take a look at our latest newsletter, our website, or our social media accounts to find something that might interest you. Again, thank you for attending this webinar, and if you have any questions during the webinar, I ask that you type them into the group chat, and Cynthia will read through those during the question period at the end of the webinar. Before turning it over to Cynthia, I just wanted to tell you a little bit about Cynthia. Just a little bit, she's got an amazing list of accomplishments. Let me tell you a little bit about her for right now. Dr. Rudin is a professor of computer science, electrical and computer engineering, and statistical science at Duke University. And she directs the Prediction Analysis Lab, whose main focus is in interpretable machine learning. She is also an associate director of the Statistical and Applied Mathematical Sciences Institute. She held positions previously at MIT, Columbia, and NYU. Her undergraduate degree is from the University at Buffalo, and she holds a PhD from Princeton University. She is a 3-time winner of the Informs Innovative Application and Analytics Award and was named as one of the top 40 under 40 by Poets and Quants in 2015. She was also named by the BusinessInsider.com as one of the 12 most impressive professors at MIT in 2015. She is past chair of both the Informs Data Mining section and the Statistical Learning and Data Science section of the American Statistical Association. She has served on committees for DARPA, the National Institute of Justice, and AAAI. She has served on 3 committees for the National Academies of Sciences, Engineering, and Medicine, including the Committees on Applied and Theoretical Statistics, the Committee on Law and Justice, and the Committee on Analytic Research Foundations for the Next Generation Electric Grid. She is a fellow of the American Statistical Association and a fellow of the Institute of Mathematical Statistics. She will be the Thomas Langford Lecturer at Duke University during the 2019 and 2020 academic year. And with no further ado, Cynthia, I'd like to turn it over to you.
Thank you. Can you hear me, first of all?
Yes, I can hear. We can hear you.
Okay, great. All right, so I'm going to talk about interpretability versus explainability. So first, I need to define what a black box model is. So I want to think about the world as it is now, where they don't use interpretable machine learning for some really important problems, and they're using, black box machine learning models instead. And these are models that are either too complicated for any person to understand, or they're proprietary, which means there's some company's secret sauce, and they hide what the calculation of the model actually is. Okay, so what happens when you use these black boxes? Well, first thing is that you could get several extra years of prison time. So this is the story of Glenn Rodriguez. It was written up in the New York Times, and he was sent to prison at a young age for a crime he committed as a teenager, and he was in prison for something like 17 years. He was a model prisoner, and then he was denied parole. And why is that? And it's because someone had incorrectly entered some information into a black box predictive model that was being used to predict whether he would commit a crime in the future. And at the parole board hearing, they just denied his parole. And there was nothing he could do to fight it because he didn't know about the error in the model until afterward when he compared a score sheet to somebody else's. And the model had 137 factors in it, so it wasn't that easy to spot an error. And this same situation happens to a lot of people with the same model. And if the model was interpretable, then it would have been a lot easier to spot the error. Okay, so what else could happen to you as a result of a black box model? Well, if you lived in California during the wildfires last year, you might have been using Google's daily air quality predictions to determine whether it was safe to go outside. And you might have seen Google's predictions that air quality was fine on days where people were also seeing a layer of ash on their cars. Because during the wildfires, Google replaced the EPA's Trustworthy Air Quality Index with a proprietary machine learning model from the company Breezometer, which claimed to be more accurate. But clearly this proprietary model was not doing what it was supposed to, and it put a lot of people in danger. And I don't know how many children went playing outside during those days, but hopefully the layer of ash on the cars would have deterred them, but who knows. All right, and this article came out this week. And so, yeah, another thing that could happen to you is that you could receive worse health care because of your race. And the article says that a hospital was ranking patients to figure out who needs additional medical attention. And the white people got higher rankings, even if they were not as sick. And the reason for that is because the algorithms were using cost information. And the Black patients were getting lower cost healthcare. And so the algorithm thought they weren't as sick because they weren't using up more costs. And so it didn't recommend them for extra care, even if they were sicker than the white people. Okay, and now, I've just given you a few things that have gone wrong with using black box models, but there's a tremendous amount more that could go wrong. And probably many things have gone wrong and I don't know about them because they were hidden. And now, people are starting to use machine learning for medical decision-making and loan decisions and self-driving cars and for all matter of other things that you really don't want to go wrong. And some people love their black boxes. They argue fiercely that they really need them. Like, I really need my black box. Anyway, so let's define here what interpretable machine learning models are. So these are models that obey a domain-specific set of constraints. I actually have a technical definition there, and just to, if you wanted to see a technical definition, but essentially it says that these models are constrained in model form so that they're either useful to somebody or they obey some kind of structural knowledge of the domain. And there's this big spectrum between fully interpretable models where you understand how all the variables are jointly related to each other, to sort of like on the other end of the spectrum, these very loosely constrained models where just like the model's forced to decrease along one variable, for instance. Okay, so what I'm going to do next is show you two examples of machine learning models that are actually interpretable, and then I'll go into the explainable side of things and contrast the two. Okay, so I'm going to give you these two interpretable machine learning models in context. So I want to go back to the Glenn Rodriguez case. And he was denied parole because, like I said, of a miscalculated score from a model. And it's a proprietary model. It's called COMPAS. You might have heard of it. It was in the news a lot. And so COMPAS is, that there's a company that runs it, and there's all kinds of lawsuits to try to keep it private and so on. And so you'd think that for a super proprietary private model that it would be very accurate. And so the question is, well, how accurate is it? And so we took the data this is data from Broward County, Florida. This is similar data to what was used in the ProPublica article to accuse COMPAS of being racially biased. But so anyway, we took this data from Florida, and what we did with it was we compared COMPAS's predictions to the predictions of our latest interpretable machine learning method from the lab, which at that time was the Corals method. Okay, so the Corals method it's a very fancy method, but it's producing decision trees. It's producing these one-sided decision trees. They're also called rule lists. And we ran Corals on that Florida data, and this is what we got. Excuse me. Okay, so that is the whole machine learning model that we got, and Corals is picking exactly which conditions and which variables to use in that model. And so the whole model, it basically says if you're young and male, predict you'll be arrested within 2 years after leaving the police station. Also, if you're a little bit older and you have a few prior crimes, predict you'll be arrested within 2 years. Also, if you have more than 3 prior crimes, predict arrest, otherwise predict no arrest. And you'd think that, that looks pretty simple, right? And so you look at it and go, well, how could that be accurate, right? How could that be accurate and, compare that to COMPAS? My goodness. But it turns out that surprisingly, they're equally accurate. So what I'm showing you are cross-validation results for COMPAS and corals. And the different colors are just different folds of data. And so you're just seeing a range of, the variance due to different folds. And yeah, they're pretty much exactly the same. And the interesting thing is that not only are they the same, but we tried a whole bunch of different machine learning methods on this data set, and they all perform the same. And some of these are complete black boxes like COMPAS, which is proprietary, and some of them are things like boosted decision trees, which is so complicated you can't even fit it on the slide. Support vector machines with Gaussian kernels, again, really complicated. And, on the other extreme is corals, whose whole model is just right there in the corner of the screen. And now there was a huge debate, as I mentioned, about the algorithmic fairness of COMPAS. But the truth is that we just don't seem to need COMPAS at all. So why are we still using it? Okay, so that's one example of an interpretable machine learning model. Let me give you another example. So this example is in healthcare, and it's about preventing brain damage in critically ill patients. And so the idea is that if you come into the hospital with an aneurysm, and the aneurysm bursts, you have a stroke, and you have a subarachnoid hemorrhage, which is right here. And then the doctors perform surgery on you, and you end up in the intensive care unit, and they put a continuous EEG monitor on you. And the reason that they're monitoring you is because you are actually in terrible danger because you could have a seizure. And seizures are very common in these patients, and they cause brain damage. Seizures can often be more problematic than the actual stroke. And the only way to detect whether you've had a seizure is with these EEG monitors, because these are not like visible seizures that you can see someone shaking. It's actually just in the brain. And so they place individuals on the EEG monitors. And what the doctors that I work with wanted to do is they wanted to predict the seizures in advance, because they want to determine how long the patients need to be monitored, and whether to treat the patients and how to treat the patients. And another, so if you're sick, you need monitoring and you need medicine. But if you're not sick, the doctors really do need to take those monitors away because somebody else needs them. And very often people just end up on the monitors for way too long, and so that deprives other people of monitors, and the monitors are expensive and limited, so you really want to do a good job making sure that the monitors are distributed properly. So we really do need to predict these seizures in advance. So we created a model with the help of the neurologists called 2 helps 2B. And this model is small enough that it can fit on a PowerPoint slide, but it is also as powerful as our best black box machine learning models. And so there's the 2 helps 2B score. And these 6 conditions, they're things that neurologists are trained to recognize. So for them, they would understand what these different patterns are that they're seeing in the EEG signals. But so the 2 helps 2B score, I don't know if you can see my mouse, but I'm moving it around. But the first line is 2H, and then the next line is E, L, P, and then S, and then 2 points for the B. Okay, so it's 2 helps 2B. And the doctors can memorize the whole model just by knowing its name. And as I mentioned, 2 helps 2B, it looks like a rule of thumb, but it's actually a full-blown machine learning model. It was not created by doctors. It was created by data fed into a machine learning algorithm. It's actually a machine learning model. It's just as accurate as the black boxes. And then the nice thing about the interpretable models is they don't force you to trust them. Doctors can decide themselves whether they want to trust it. And also the doctors can calibrate the score with information not in the database. Like there might be unusual circumstances that might cause a doctor to adjust how they care for the patient. And also the score can be explained to non-physicians, right? You can explain to somebody, okay, you take these points, you calculate the total score, the score translates into a risk. And, you can explain to someone why they're being, why somebody is being taken off of monitoring, EEG monitoring, for instance. And so the way that it would be used is that you'd come in with your aneurysm, it would burst, you get the surgery, and then the doctor is monitoring you and takes a look at your EEG signal and says, oh, you have a high 2-HELPS-2B score, so we need to place you on monitoring for a long time and start you on medicine right away. Okay, or else the doctor would say, oh, you're very low risk and we should take the monitors away after 24 hours or something like that if nothing else happens. Okay, so far, 2-HELPS-2B it's developed with data from Massachusetts General Hospital, and it was validated on an independent multi-center cohort from several other hospitals. And what I'm showing on the horizontal axis here is the predicted probability of seizure from 2-HELPS-2B, and then the observed probability of seizure on the vertical axis. And you can see that it's fairly well calibrated even across the different hospitals. And it's been implemented in 2 hospitals right now, Wisconsin and MGH, and it's ongoing implementation in several other hospitals. And so far it has, in fiscal year 2018, it's resulted in a 63% reduction in the duration of monitoring per patient, which has allowed the neurology unit to monitor over 2.8 times more patients, which is a really big deal for them. They can monitor almost 3 times more patients, which really makes a huge difference and helps prevent brain damage and so on. And it's saved a few $million, but the really important information that the doctors consider is the fact that they can monitor more patients than before. That's what they're really interested in. Okay, so let's talk about some technical aspects of 2-HELPS-2B. So it optimizes interpretability, right? The point scores and everything, that's all optimized for interpretability, but never at the expense of accuracy. You would never want to sacrifice accuracy to gain interpretability, but luckily we don't need to. There are, if you think about the complexity of the problem that 2-HELPS-2B is the solution of, right? We had a lot of variables, and if you consider the possibility of, our point scores are 1 and 2, but that was chosen by the algorithm, and it could have chosen, 0 up through 9, say, and in fact, if that was true, then if you tried to enumerate every possible score, then it could take you maybe until the end of the universe to do it, and that's probably not a good idea. So I'm just showing you, like, these are some of the variables that we had. So it had to choose from quite a lot of variables. And, the problem actually falls into a pretty bad category when it comes to computational hardness. So for those of you who know this stuff, it's a mixed integer nonlinear program whose feasible region is the integer lattice. So it's really quite hard. Okay, so as I mentioned, it's optimized for these sparse integer coefficients. It looks like a person made it up, but that's done on purpose, right? And it's nice because the doctors can validate it using their domain knowledge, and they don't need a calculator to use it. And also the probabilities are nice and evenly spread out along the axis here. And again, like, they go up as the score goes up. So as the 2-HELPS-2B score goes up, the probabilities go up. And all of this is all done by design. It's all part of the design and the optimization of 2-HELPS-2B. Okay, so I gave you 2 examples of interpretable machine learning and how they might be important to know about or use in practice. And I want to talk a little bit about explainable. So explainable is totally different than interpretable. They're very different. There's a chasm between these 2 things, and most people think they're the same, but they're not. So interpretable machine learning does not use a black box. There is no black box. There's no elephant in the room. There's no black box. In explainable machine learning, you start with a black box, and then you try to figure out what it's doing or what it might be doing. I call this poking at the black box. Okay, so the idea is that you start with a black box, and then you do something. Like you might create a local model that approximates it, or create or you could create a global model that approximates the black box, or you could compute the derivatives of the black box in different directions. Like a lot of the explainable machine learning papers are just like, oh, we took a derivative of the black box in this direction, and this is what happens, and so it's sensitive to this. Also, some people visualize just what part of the input the model's paying attention to, like they just show a neural network and they say, oh, it's paying attention to this part of the image, so it must be doing the right thing. But that's not necessarily, it's not necessarily true. Okay, so why are these two things not equal? Well, if you think about it, if you work with a black box model, if you train a big machine learning model in some big database, then if you use that black box to make predictions, then the problem is that you end up trusting the database it was from, right? I mean, I don't mind trusting complicated computations, like a computation from a complicated formula. Okay, fine, I have no trouble trusting that. The thing I don't want to trust is a database, because every large database I've ever seen has had something terribly wrong with it. Okay, so if you trust a black box, it means you trust the database that it was built from, and I don't. And then double trouble is this problem where you now rely on two models instead of one. You have the black box and you have the explanation model. And these two models necessarily disagree with each other, because if they don't, then they always agree with each other, which means you don't need the black box, because the explanation is exactly the same as the black box. So they must disagree with each other. And if they disagree with each other too often, then you can't trust either one of them, because if you think about it, some people say, oh, well, my explanation, it's right, my explanation model is right 90% of the time. The problem is that it's wrong 10% of the time. So then you can't trust the explanation, and then you can't trust the black box. So you're actually in a worse place than where you started. Another problem with black box is that typographical errors are very common. So for instance, with the COMPAS model that we were talking about earlier in the Glenn Rodriguez case, those kind of typos appear all the time. And then also, if you can produce an interpretable model, why should you explain a black box? I already showed you an example where, there's a model that's used throughout the justice system that's a black box. Why do we need it? I mean, we can get a set of very simple rules that performs just as well as it or any other machine learning method. So, why should we explain a black box if we can replace it, right? Why should we give more authority to the black box by claiming that we can explain it rather than simply replacing it with something we don't need to explain because it explains itself? Okay, so I want to talk a little bit more about this, the idea of local explanations. All right, or global explanations, really. Okay, so a lot of times people use the word explanations in a way that doesn't really make sense. It's not actually an explanation. So the word explanation, I think it kind of started with some people writing a paper where they instead of using the word approximation, they use the word explanation. So it's like, oh, I know what the model's doing. I explained it by creating this approximation. It's like, no, that's not an explanation. That's an approximation, because approximations don't necessarily even depend on the same variables as the black box. So for instance, I've drawn let's say the black box is f of x, which is this curvy function here. And this depends on, let's say it's a criminal recidivism prediction model, and it depends on age and the number of prior crimes, and that's all it depends on. Okay, it's just some function of age and the number of prior crimes. And then it could happen that you could create an approximation model to the black box that depends on race. And because you see, race is correlated with age and number of prior crimes. And so you could actually get confused that the black box model depends on race, even if it doesn't. Okay, so you could say, well, this seems like a silly thing. Nobody would ever make this mistake. It's so obvious. But it might actually happen. And in fact, it actually did happen. And I'll talk about the famous ProPublica article. This paper probably began the fairness and interpretability, not interpretability, the fairness in machine learning literature, I would say. And this paper accused that COMPAS model of depending on race, age, and, well, age, prior crimes, and race. So they accused the model of depending on race, even conditioned on age and criminal history. And so I looked at this article when it came out, and I had done some work on recidivism prediction, and I thought, this is really strange. This doesn't, why would they create a model that depends on race? It doesn't make any sense. But luckily, the ProPublica article gave us this data that I mentioned from Broward County, Florida. And so we actually had COMPAS scores, and we could investigate whether the ProPublica analysis was right. So let me tell you what they did. So what they did was they showed that the false positive rates and false negative rates varied by race, and that makes sense. And they knew that was, kind of not a great way to do the analysis, because they said that we should condition on age and number of prior crimes, because the white and black populations differed by age and number of priors. Okay, so you could even identify even if you had a model that only depended on age, you'd still see differing false positive and false negative rates. So they said, fine, we'll condition. And then after conditioning on age and number of priors, they still found a linear model with a low p-value for the race coefficient, indicating that the race coefficient was non-zero. And so they concluded that COMPAS depends on race. Okay, so let's try that again with a little bit more commentary. Okay, so they showed that false positive and false negative rates varied by race, and they knew that this was a property of the data and not necessarily the model. Like, as I told you, in Broward County, the blacks in the database are younger and they have more priors. So they said, okay, we're going to condition on age and number of priors. And that's a good idea. I agree with them on that. So then, as I mentioned, they then created a linear model that approximated COMPAS with a low p-value for the race coefficient. And the problem with that is that I don't think COMPAS is actually a linear model. COMPAS is a non-linear model, and so their conclusion ended up being wrong. Okay, so this is what happens when you create an explanation model. This is what happens when you create an explanation model for a black box and you do it wrong. You make a conclusion that the black box depends on different variables than it actually does. Okay. So let me give you a little bit more detail about this, because we've been working on trying to understand what happened with this for a while. Because, if I'm going to claim that these very simple models are, good for recidivism prediction, then at the very least, I would like to know what's in the black box. If they're going to defend this thing in lawsuits, I really want to know what's in it. So we think we've uncovered a little bit of COMPAS's secret sauce, and so I'll show you what that is. I think it's an important piece of it, actually. All right, so our conjecture is that the COMPAS general recidivism model is a nonlinear additive model, and its dependence on age is approximately a linear spline. Okay, so we don't think it's linear, we think it's actually a linear spline. And this is for the general recidivism model, and we think there's also a linear spline for the COMPAS violence score. There's actually two COMPAS scores there's actually a whole slew of COMPAS scores, but the two that we have are general and violence scores. And we think that they have a nonlinear dependence on age. Okay, so how did we figure that out? I mean, the model's proprietary. So how did we get that conjecture? And the answer is we plotted the data. So what I'm showing you here is a scatter plot of the COMPAS scores versus age for all the individuals in Broward County, Florida in that data set. And I don't know if you can see it, but there's like, so there's a few people, there's like a couple of people, these 1, 2, 3, 4, 5, 6, 7, 8, whatever people that don't agree with the conjecture, but everybody else agrees with the conjecture. And you can see the linear spline right there, which is that red linear spline. And the people who land right on that thing, they're people who have the lowest score for each age. And also these people, the people on the curve here, they don't have prior criminal history. And there's nothing in their record that would indicate additional COMPAS scores, and COMPAS should only have positive contribution to the score. So we think that these are the lowest COMPAS scores for each age. Okay, and so this is the, by the way, this is the general COMPAS score. It's the violence score on the right and the general score on the left. And I'm going to zoom into these curves here, right here. And what you're seeing is that you're seeing how we constructed the linear splines. And what you'll also see is that these are not linear, right? And if you try to approximate them with a line, then it's particularly bad at lower ages. And there's a lot of people in those young ages in the data set. So a linear fit is particularly bad. So we were thinking, okay, ProPublica's analysis is not right. But also the COMPAS manual seemed wrong because the manual said that it had a linear dependence on age. So we were trying to figure out whether COMPAS depends on race, just conditioned on age and criminal history. So what we did was we subtracted off what we think is the contribution of age to COMPAS, which are those linear splines. And then we ran machine learning methods with and without race to see if they need race to predict the COMPAS score well. And what we got, I'll just tell you the conclusion here. This is the results, but these tables are kind of difficult to digest. And so what I want to show you is the fact that the only thing you really need to see on this plot is the fact that these pairs of numbers are very similar to each other, because these pairs of numbers are different machine learning algorithms run with and without race. And if they're similar to each other, then that means that the model is not, you know, that if you run it with race and without race, you're getting essentially the same accuracy. Okay, so far, I'm not seeing any indications that COMPAS is necessarily depending on race, other than through age and criminal history, which are the main factors that we have in our machine learning models. Okay, so as I mentioned, approximations are not explanations, and it's kind of too easy to make this type of mistake, right? I mean, ProPublica, for instance, ProPublica is always cited for their wonderful analysis on this project, but the truth is that the statistical analysis on this work is totally bogus, and I don't know why we keep citing them. And I think maybe it's because race is a topic that really fires people up, but this particular project is bad science, and we should treat it like that. All right, so we've decided that it's really hard to analyze black boxes without messing up, but perhaps we don't need black boxes at all. So I've been trying to investigate this, this trade-off between accuracy and interpretability, and I actually do think it's a myth that there's necessarily a trade-off between accuracy and interpretability. And I'm saying that after having worked in many different application areas. And lately, we've been working in kind of an area where black boxes rule, like an area of machine learning where people really think you need a black box. And that's computer vision. Because, computer vision is where the deepest of the deep, neural networks originated, and where these models are the king, right? These are some of the most complicated models on the planet. Okay, so let's talk about computer vision for a minute. So computer vision is complicated because the images are data that lie along a very narrow manifold in pixel space, right? So if you walk along the manifold of natural images, you see natural images. But if you change even one pixel, you step off the manifold, right? So this image with this one pixel that's wrong, that is no longer a natural image. And so analyzing data like this is actually very difficult to build models for image data. And so I thought, oh dear, this is going to be quite a challenge. But I didn't want the computer vision people to tell me that it's impossible to have an interpretable deep neural network. So I figured we'd try to construct one. So the way we did it was to try case-based reasoning, because you can't build a decision tree on pixel space. That doesn't make any sense, right? So we thought maybe case-based reasoning would work. So case-based reasoning is kind of similar to nearest neighbors, and it's what real estate agents do to price houses. Like if they're trying to price your house, they'll say, oh, there's a house in your neighborhood that's kind of similar to yours in this way, and there's another house that's, you know, in a different neighborhood, but it's similar to yours in that way. And so they kind of bring together these different cases, past cases, to try to make a prediction for the current case. You know, what's going to be the price of your house. So I want to show you some results from this interpretable deep neural network. And this is the network explaining to me why it thinks this bird on the left looks like a clay-colored sparrow. And I love working on the bird watching data because I know nothing about birds. And so I can get the network to explain it to me, which is great. Okay, so this bird here, the network's going to explain to me why it thinks it's a clay-colored sparrow. So the network says, okay, I think this part of the bird over here looks like, you know, the head part of the bird looks like this head of this bird over here on the top right. And that's why, you know, that's part of the reason I think this bird is a clay-colored sparrow. And then it says, oh, look at this part of the bird, you know, that part, which looks like the belly of the bird. And then this part looks like that part of this bird, which is this is a prototypical clay-colored sparrow. And then these feathers, those look like the feathers of this bird, which is also a prototypical clay-colored sparrow, and so on. And so it's saying to me, I think this bird looks like a clay-colored sparrow because this looks like that, and this looks like that, and this looks like that, and this looks like that. And so we said, okay, well, since the network is doing this looks like that, we will simply call the network this looks like that. So that's what it's called. It's called this looks like that. And the way the thing works is that you take your favorite black box, you know, your favorite convolutional deep neural network, whatever you want, and you take your favorite black box and you put in an extra computation at the end to make it do this case-based reasoning. So you get, you know, most of the complexity of the black box, but you also get the interpretability of being able to say that this looks like that. And training this thing is a beast, but it really works. So I'm going to show you a little bit more about the computation that it's doing. So this network is trying to tell you why it thinks that this bird is classified as a red-bellied woodpecker. I don't know why it's a red-bellied woodpecker because it looks like it has a red head, but that's what it is. It's a red-bellied woodpecker. Anyway, so it's telling you that it thinks the head of the woodpecker looks like the head of this woodpecker here. And this is a prototypical red-bellied woodpecker. And then it gives a similarity score. So here the score is a 6.499. So that's the similarity score of our bird's head to the prototype's head. And it says these are very similar looking, like strikingly similar. So I'll give it a lot of points, right? Similarity score is really high, 6.499. And then each of the prototypes gets a score that tells you how important that particular prototype is for defining the class. So this top prototypical red-bellied woodpecker, that has a class connection score of 1.18. Okay, and then these things get multiplied together, and it gives you some number of points that the similarity of this case to that case is going to contribute to the final score. Okay, and then it's saying, all right, well, look at the feathers of this bird. Those look like the feathers of this bird, and this bird is a prototypical red-bellied woodpecker. And I'm going to give it 4.392 points because it looks very similar. And then I'll give it the class connection weight for this prototype is 1.127. Okay. And it does this, there's actually 20 prototypes per class. So the computation is, it's, you know, there's 20 of them. And then they get added all together. And the total number of points for the red-bellied woodpecker class is 32.736. Okay, so then the network's told me why it thinks it's the red-bellied woodpecker, but let's look at the next highest rated class, which is the red cockaded woodpecker. And here, since the red cockaded woodpecker isn't actually red, then the network can't gather the information, right? there's nothing to compare the heads to because the heads don't look similar to each other. And so it can't get any points for the similarity of the head. I mean, the only thing it can really see is that the feathers look kind of similar to the red cockaded woodpecker's feathers. And so it's using that as much as it can to gather as many points as it can, but it's only getting 16 points, whereas the other one's getting 32 points. And so that's why it thinks it's a red-bellied woodpecker. Okay, so this data set that we're using, the birdwatching data set, it's a very famous data set. It's a benchmark in computer vision. People still use it. It has 200 classes of birds. Some of the pictures are very, very difficult to tell apart because some of the birds are really far away and they're flying and they're in the shadows, and it's just a really difficult data set to work with. Now, if you run a whole bunch of the different standard deep convolutional neural networks like VGG16 and ResNet34, we ran, I think, about 6 or 7 different of these standard networks, DenseNet and so on. So the original black box accuracy was somewhere between 74.6 and 82.3. And then when we put the this looks like that piece on the end of these networks and retrained them, we're actually getting right in the same range. I mean, we lost a couple points at the top end, but we gained a couple points at the bottom end. And this is just, the training of neural networks is very finicky and difficult. So, so that's what explains that variation. But we found that if we combined all of these networks together, then we actually got accuracy of 84.8%, which is that's about the same accuracy as like the top deep neural networks on this data set presently. Like that's, beyond what we're getting with any of the baseline black boxes. And also, when you combine the interpretable networks together, you still get an interpretable model because you just add up. It's just more prototypes because you just have prototypes from all the different networks. And so, yeah, it's still interpretable. Okay, so I have yet to find a domain where I actually need a black box, because if I can do this for medicine, criminal justice, computer vision, and whatever else, it's just not clear to me that you can't add interpretability constraints and still maintain your accuracy. So last summer, I found out about a competition. I found out just from talking to somebody, and it was called the Explainable Machine Learning Challenge. And I was wondering if I finally had met my match, right? So the goal of this competition was to create a black box and explain it. And the data set they gave us was from FICO. It was a credit risk data set. And you had to determine whether each person in the data set would default on a loan. And we got the data set, and I took one look at it. It was a nice big data set, but I looked at it, I just glanced at it, and I thought, I can't believe it. They gave us an ordinary data set, and it had a good data representation. And I thought, could I be wrong? Could it be, a problem with a good data representation where you actually need a black box? And so I said to my students, go take that data set, go take this data set, go try running a whole bunch of algorithms on this data set with varying levels of complexity. Try a deep neural network, try whatever you can, try everything, and see whether they all perform the same. And so a day or so later, they emailed me and they said, yep, all the models are performing the same. And so we pretty much knew that at this point that we could construct an interpretable model with the same level of accuracy. So everything was getting about 73, 74% accuracy. And so I brought the students into the room and my other colleagues, and we said, okay, what are we going to do? We either play by the rules, create a black box and explain it, or we ditch the black box and create a model that's inherently interpretable. And so, risk losing the competition. And so we decided that since this was credit risk, that this is an important topic and we needed to create an interpretable model, and we didn't really care if we lost the competition. As it turns out, yeah, we lost the competition. I was right. The judges had no idea how to judge this, and we totally bombed. So let me show you a little bit. Let's see. I wonder if that link works. So if I click that link, okay. Can you guys see this? Can you all see this? What I just clicked and brought up? Let's see here. I can't tell if you can see it. Yes, okay, good. Great. Nothing happened when I clicked. That's bad. All right. Something did happen when I clicked. All right, let me try to share that. All right, let me go here. How can I share the whole thing? You share. Share the desktop. Oh, I'll share that. Good. Share. Share the desktop. Good. Share. Got it. Can you see it?
Yes, now I see it.
Oh, good. Okay, so this website is public, so you can just go here if you want to. But what we did was we took the FICO data, and so I'm just showing you, this is a list of the features, and you can adjust the features if you want to. Oops. There, we can adjust it this way. Sorry, you actually have to adjust it. You can't just click on it. I don't feel like entering information into 40 of these boxes, so I'm just going to use one of our demo people. And then when I click this run model, it's actually going to run CPlex on the Duke machine, and it's going to calculate the model for our person. And so what we did was we grouped the different features into different categories. So each person would get a risk score based on their, like, this is the delinquency subscale, and it's essentially a sparse logistic regression model. And so it's telling you that, you know, the percent of trades never delinquent was pretty bad, and so you get a point for that. And then the month since most recent delinquency, oh, you had a recent delinquency, that's, you know, well, no, it's 0 to 17, so you lose points for that. Okay, max, whatever features. So you gain points and lose points for different aspects of your credit history. And they told us, they gave us monotonicity constraints that said that, oh, the model has to increase along this variable and decrease along that variable. So we made sure to get that all right. There wasn't anything nonsensical in here. And then, you know, install burden, install trades. You know, there was a separate subscale score for that. This is essentially a bunch of stacked logistic regression models. I mean, we made it look like a neural network because we wanted them, I mean, they kind of were, like, their website had neural networks all over it, so we wanted to make it look like a neural network, like a 2-layer neural network, but it's actually a bunch of stacked logistic regression, sparse logistic regression models. And so there are 10 subscale scores, and they're colored by risk. So in other words, the contribution to the risk. So in other words, the person actually, his utilization was fine, so he didn't lose any points for that, but his delinquency was quite bad, and his trade open time was pretty bad, and so on. And so that's where he gained points. And so in the end, he had a really high risk of default, 95% risk of default. And this again was just having the risk score from all the subscales, the 10 subscales, each weighted. So this column multiplied by that column gives you the points, add the points up, send it through a sigmoid, and that's the risk. Okay, so every single computation here is visible. It's not a black box. You can see exactly where you lost the most points and what those points were lost for. So we provided this interpretable model. We also had a whole bunch of other, like, different types of explanations of this interpretable model, but I think they just ignored that. I think they were just, we wanted them just to look at the visualization tool. But unfortunately, they didn't, they didn't actually allow visualization tools, but they didn't say that until after the competition went, so that didn't that didn't go so very well for us. Can you see, are you back to my PowerPoint here? Can you see my PowerPoint?
Yes.
Yes. Okay, good. All right, so anyway, it was really embarrassing because they announced the winners, and then I had to immediately, like, literally, I was the next talk right after that. And so I was really upset, and I did my best to kind of say to the judges, but you don't need a black box for this data set, blah, 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 blah. And so the judges kind of, I was surprised that they actually kind of listened to me, because they actually went back and thought about how they judged the competition. And then they realized that, that this was actually, that what we had sent them was actually kind of cool. And so they designed a special prize for us. So they created a prize. So they created this FICO recognition award that acknowledged our submission for going above and beyond expectations with a fully transparent global model and a user-friendly dashboard. And I was so happy about this because I thought, oh yeah, they're actually listening to me. This is great. And then I got really excited about this and decided to take the paper that we wrote about the competition and send it into the special issue of a journal. It was a very prestigious journal. And I was told before I sent it into the special issue to send an email to the editor of the special issue to see whether the paper was in scope. And so I sent an email to this very prestigious person at this very prestigious university. And I said, dear professor, so-and-so, we wrote this paper, it's about this competition, and we don't know whether our paper fits into the scope of the special issue. It's not a traditional methodology paper, it's an analysis of this data, including an interpretable model, and it won this award, and would you consider it, please, for your special issue? And the guy writes back to me and he goes, dear Cynthia, thanks for reaching out. This is an interesting paper, but I'm afraid it's not a good fit for the special issue. It's also related to my own recent work on explainability of neural nets. Is that data available? If so, could you share it? And I was like, oh man. I was thinking, I sent the guy a paper saying, you don't need a black box for this data set. And he sends me back an email saying, I don't care about your work, but can you send me the data so I can create a black box for it and explain it? And this is unfortunately the state of where things are at the moment. And I tried to help remedy the problem. Like I tried to help solve this by writing this paper, just a perspective piece and giving some more reasons and outlining all these things about why we should consider making interpretable models instead. But, I don't know. Oh, by the way, this paper, I should say, it had please in the title when I started. So, and they made me take out the please. So it sounded more commanding, like, stop explaining. But it was actually, please stop explaining. Anyway. Okay, so I outlined a bunch of reasons why you should use interpretable models instead. And, we'll see where this goes, I guess. So I thought I would end with some of my current challenges here. I want to encourage policymakers not to accept black box models without significant attempts at interpretable rather than explainable models. And I'd like to continue to design different kinds of software that makes it easy for data scientists to construct interpretable models with provable guarantees. So if you don't have provable guarantees, you're back where we were in the early 90s with CARD and C4.5, right? You just have heuristics. But for the models that I showed you, like the linear models and the decision trees that I showed you, those models are provably optimal with respect to some trade-off between accuracy and sparsity. So all of them are really, solve very difficult combinatorial optimization problems. And we know that this is the best model of this class. I'm hoping to provide some better educational tools on interpretable machine learning because right now everyone and their cousin has been writing a review paper on explainable machine learning and it's all rubbish. And anyway, I was hoping to work on that soon, although admittedly I have not had time. And then I'm also hoping to try to create some compelling arguments to combat the prevailing belief that there's a sacrifice in interpretability required for optimal accuracy. So my latest approach to this, I've tried all kinds of stuff, right? I've tried creating algorithms that are equally accurate to the black boxes. I've run, algorithms on these competition data sets and showed they could be equal to the black boxes on all these different data sets. And so I thought we would, and that includes like computer vision and healthcare and criminal justice and so on. And so I thought, why not try a mathematical argument? So I'm actually working with some of my colleagues to try to prove that for many data sets that are reasonable and have certain properties that interpretable models that are equally accurate to the black boxes, that they must exist. All right, thank you very much.
Thank you so much, Cynthia. This is Kristen Foley. I'm playing tag team with Susan today. I'm from the NCASA. So if anybody had questions for Cynthia, if you want to type them into the chat, and then we can take a look and see if Cynthia can respond in our last couple minutes here. while we're letting people come up with ideas, I was curious if you were able to look at who did win the competition in their black box and how different it was, kind of the how different it was from versus the model you came up with, where there really striking differences.
Well, the winners, they just created these rule-based, things, like if the person, because the person had this characteristic and this characteristic, that's, that's why the model, that's why the model would predict that they would default. So the judging team didn't really know what they were doing. So the way they judged it was to have the explanation print out, because this and this, then I think X. And they blocked out the X and had the judges try to predict what the X was. And so if the judges could predict what the X was, then they claimed that this was a good way to judge the competition. I don't think that's a good way to judge the competition at all, because that doesn't really model the fidelity of the explanations. And so, how good are these explanations at explaining the black box? So I didn't think it was a good way to. That competition had a lot of problems. It was fun to participate in it, but the thing is, a lot of competitions have a lot of problems. I mean, people don't know; they don't always know how to judge these things when they set them up.
Well, yeah, it's really interesting that you got their attention, though, by trying to break the rules on purpose. I think that's really interesting result. We did have one question. It says, how did you construct an interpretable model?
Oh, so we constructed these sparse logistic regression models. Let me bring it up. Let me bring that up again. I'll start the share again. Oops. Okay, hold on. Have that. There's the competition site. Okay, share. Share desktop. Share. Okay, so let's take a look at these models. So this is, do you see how it's sparse? It has only 1, 2, 3, 4, 5 real terms. I mean, these -7, 8, and 9, those were like special features. So we had to figure out where the cut points were, and then it's literally just logistic regression once you figure out where the cut points are. And the cut points, those were not that easy to figure out, but we had our own method for doing it. It wasn't very fancy or sophisticated. We were working very quickly. I mean, we had very little time to do this, because we found out about it only like, I think, a month before the deadline, and then they extended the deadline by a month, and we were like, oh, thank goodness. So yeah, it was very quick. Yeah, so we basically grouped the features by their meaning, like we put all the delinquency features together, we put all the installment features together. Yeah. Okay. Yeah. So anyway, yeah, it is an additive. It's not actually additive, because it's actually a tool. There's actually a nonlinearity. You see, so when you get the number of points, you add a bias term to it, and you send it through this nonlinear function, and you get a risk score just for that particular subscale. Okay, so here the risk was 81.9%. And then the results, all of these percentages, so this is 81.9, 78.9, 74.2. Those were the input to the next logistic regression model. So it was not linear. There was a nonlinearity in it, but it wasn't trained like a neural network. I mean, it was trained like logistic regression models once we figured out where all these cut points were supposed to be. And those we figured out based on distributions of, we were looking at plots of the probability of default as a function of each of the attributes. And that's how we figured out all those cut points. So this was not like heavily optimized like all my other, like the model that I showed you for the EEG project. That was heavily optimized. And then the decision tree models, those are all heavily optimized. But those were more long-term projects. Okay, so I've sort of answered this question about GAMS. Do you all use GAMS for interpretable? I think maybe she meant, do we always use GAMS? No, we use decision trees very often, which are nonlinear. If not, why do we focus? Okay, so we also use the case-based reasoning for the neural networks. So yeah, it's usually some combination of GAMS, so additive models, decision trees, or case-based reasoning. There's not too many other forms that I know of. Yeah. For at least for supervised learning with, yeah, supervised learning. Is the code we use for the competition model available? Well, the model is available. The code is probably not, because there was a lot of manual. I mean, we were doing this under time pressure, and we were fiddling a lot with it. But the code for all of the other methods is available. So I'm still sharing my screen, right?
Yes, you are.
Okay, so let me see if I can just go to my website. Yeah, so I have part of my website it's just code, and we have code now for optimal sparse decision trees, and then the interpretable neural networks that I showed you, and then like this extends it to hierarchical prototypes. And the summary explanations is from the FICO competition. That was for one of the explanation methods we used for we explained the interpretable model. So we provided code for that. Yeah. And then this is for matching and causal inference. That's also interpretable. This is all interpretable decision lists. This is the certifiably optimal rule list that I talked about, where it's doing the decision trees, one-sided decision trees. Yeah.
Oh, that's great. Thank you again. We're right at the top of the hour, but a really interesting presentation. And we will be posting this on our on the NCASA website. So if anybody wants to go back and listen again later on. So thank you so much, Cynthia.
My pleasure.
Thanks, everybody. Have a good weekend.
Bye.